Good evening, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. Today's talk is by Professor Anirudh Sivaraman, and he will be speaking on programmable networks, hardware, software, and applications. Professor Sivaraman is an assistant professor at NYU's Computer Science Department in the Courant Institute. His recent research has focused on hardware, system software, and applications for programmable networks. He also works closely with the P4 community, Barefoot Networks, which is now a part of Intel, and Clockwork. His past research includes work on congestion control, network emulation, and network measurement. He received the MIT EECS Department's Frederick C. Henny III Teaching Award in 2012, the IETF/IRTF Applied Networking Research Prize in 2014, the ACM SIGCOMM Best Paper Award in 2017, the ACM SIGCOMM Doctoral Dissertation Award in 2018, the Amazon Research Award in 2021, and the Google Cyber NYC Research Award in 2023. Before coming to NYU, he received a PhD from MIT in 2017, an SM from MIT in 2012, and a BTech from IIT Madras in 2010. Before I move on to the talk, we would like to request the audience to subscribe to our Google group for information on our future talks. You can also visit our website for more details. I'll be pasting the link in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may raise your hand, unmute yourself, and ask directly, or type them in the chat box. We'll relay your questions. Over to you, Professor Sivaraman.
Yeah, thank you so much for having me, and thank you all for being here. Can everyone hear me okay?
Yeah.
Okay, cool. So let me just share my screen. Can people see whatever is on the screen?
Yes, it's working fine.
Cool. Sounds good. Yeah. Yeah, so I'm going to be speaking about programmable networks through the stack, the hardware that makes such programmability possible, the system software to program such devices, and what you can do in terms of applications with such devices. And this reflects work over the last 3 to 4 years with many students who did much of the heavy lifting and several collaborators at NYU and elsewhere. Okay, so to set context for this work, if we look at the internet, the reason it succeeded was it provided this one primitive across all of its constituent subnetworks, and that's this idea of best effort packet delivery. There are really no guarantees on this delivery. Packets can be arbitrarily delayed or dropped, but it was simple enough that it could be implemented across a wide range of networks, from satellite links to high-speed data centers. And this allowed the internet to proliferate and become this global platform. And this in turn made it an attractive substrate on which to base a whole number of applications that we've more or less taken for granted today. Yet, at the same time, today's challenges demand that the network go beyond just moving data from one point to another, as useful as movement of data itself is. But today's challenges demand network flexibility. And I'll talk about two drivers for this, one that has already been happening for probably the past decade and a half, and the other that is sort of more emerging at this point. So the first driver that's been already ongoing is the mainstreaming of cloud computing. And in this context, there are really two networks that we're talking about. There's the physical network operated by a cloud provider like Amazon or Microsoft, where their view is one of server boxes and switches and cables. And then there's the virtual network, where cloud tenants, it could be a Fortune 500 company, it could be you and me, they have virtual machines that communicate with each other, and there's some policies that forbid some pairs of VMs from talking to each other and allow some other pairs to talk to each other. And in this context, the physical network must be reconfigurable so that it can support these different virtual network views seen by different tenants. Okay. It's also turned out to be a good way for cloud providers to provide value-added services and differentiate themselves. For instance, you could have hardware support for a better transport protocol or a better congestion management scheme, and that could be exposed to cloud tenants through specialized VM offerings. So that's part of the reason why the physical network must be reconfigurable or flexible in this context of cloud computing. The other more emerging driver, again, this has happened over the last decade or plus, but its implications for networking are only now becoming clear, is the rise of scale-out computing, where handling larger and larger data sets and machine learning models, coupled with the availability to rent out VMs as needed on the cloud, has resulted in a whole host of applications becoming distributed. And here, there's a significant opportunity to improve applications when the network doesn't just deliver data, but also acts on it as soon as it's produced. And I'll talk about a few examples of these. So let me illustrate these two drivers with two very simplified examples. So let's say you have 4 physical server machines connected in a tree topology through 3 switches, and somebody schedules a bunch of virtual machines on top of these. Each color represents a different tenant. So all the blue tenant sees is 3 VMs with addresses A, B, and C. It doesn't know about the existence of the green and the red tenants, and it lives in its own made-up illusionary world. Now, A might want to send a packet to B inside that tenant's worldview, and somehow it needs to get to the actual location of B. And the layer of software that does this is the virtual switch, which takes packets coming from A and realizes that B is sitting on top of physical server 2, and it adds an outer header pointing to 2. The physical network knows how to route to physical servers, so somehow the physical network gets it to 2. And at this point, the virtual switch at 2 takes over, throws out the outer header 2, and just delivers it to B. Now, for those of you familiar with networking, this is a very common technique called encapsulation, but this is just part of a much broader pattern, where virtual and physical switches are increasingly this programmable platform to introduce new features. Virtual networks are the example on this slide, but there are several more examples. So in my own work, we've looked at how to handle congestion by holding packets at virtual switches if the core of the network is congested, how to export queue sizes for measurement to telemetry systems or for congestion control, and how to flexibly schedule packets when a link is ready to transmit packets in ways that make sense to a particular application. So the second driver is distributed applications, and perhaps the best known example today is distributed ML. And here I'm interested in the communication implications of distributed training. And one pattern that shows up quite frequently is this notion of an all reduce. So what all reduce does is, let's say you have 4 servers with 4 values. At the end, all servers must end up with the sum of the values. So how do you go about doing this? Same topology as before. The first server can send its value to the second server, to the third server, to the fourth server. And similarly, the second, third, and fourth servers can repeat the same process, and you end up with a whole bunch of arrows. And at this point, all of them have all 4 values, and they can add it up. But can we be smarter about this? That's the question. So let's say that the switches have the ability to add 2 packets and add some part of 2 packets, create the result and put it into a new packet and send it out. With this additional capability, we can implement all reduce a lot more efficiently. So the middle layer of switches can add up the values from the bottom 2 servers, and recursively you can do this at the top switch, and then the sum can be broadcast down the tree. And in fact, there are research results from others that I had nothing to do with that illustrate how network support for things like addition, and simple arithmetic can help speed up distributed ML. And again, this is part of a more general pattern where, as I will discuss later in the talk, network flexibility can improve distributed applications. The particular examples I'll highlight are distributed consensus and cloud-based stock exchanges. So with all that in mind, the vision for much of my research over the last several years has been, just like the internet commodified global best effort connectivity, can we do the same for flexibility, where anyone using a network should be able to customize it to their needs? Okay. So the way I approach this vision is to start out with questions of foundational interest to programmable networks. And in trying to answer these questions, I draw on a variety of different areas. And this makes research also quite a bit of fun. Distributed systems and network algorithms provide applications of programmable networks. Operating systems and compilers provide system software techniques to develop good system software for these networks. And computer architecture gives us the underlying horsepower to develop fast and programmable network devices. And this has been my approach to research, where I try and combine my perspective on the network as a flexible platform with the skills and expertise of my students and collaborators in these allied research areas. I see there's a question on chat. Okay, so that's just the
No,
link.
please ignore it.
Okay, no worries, no worries.
Google Group
Yeah,
link.
I'll keep going. Okay, yeah, I should say, just feel free to interrupt at any time. So I'm going to discuss 3 themes in this talk to give you a sense of the different layers in the programmable network stack. So at the lowest layer, the theme that I'm going to discuss is that judiciously designed new hardware allows us to get both high performance, which in the context of packet processing is achieving line rate guarantees, plus flexibility in some dimension. And the specific thing I'll zoom into is the ability to support multiple programs running on the same programmable NIC or switch pipeline. So one level up, when building compilers and operating systems for this kind of pipeline, or really any programmable network device, even if it doesn't have a pipelined architecture, the research theme that we've been following over the last several years is that solver packages, meaning turnkey software that allows you to solve integer linear programs, SMT, program synthesis, these packages will play an important role in designing compilers for packet processing hardware. And finally, network flexibility can enhance distributed applications. And here I'll talk about a particular new multicast primitive that we've developed based on synchronized clocks. And I'll show you how that multicast primitive can be useful for distributed consensus and fairness in the context of stock exchange. So time permitting, I'll touch briefly on something that we're currently working on and I'm particularly excited about, which is that the next step in programmable network hardware is up the stack, where instead of processing one packet at a time, we're going to start thinking about processing one piece of data that is of direct use to the application, like a remote procedure call that might actually consist of multiple packets. So we're going to be using application data units, to use an old term from networking, as the fundamental unit of data processing instead of packets. And in this context, we're developing a programmable RPC processor and its associated software. We have some very preliminary results on this that I'll briefly touch on. Okay, so let me zoom in to the multi-tenancy piece. And the vision for this work was, wouldn't it be nice if we could have packet processing as a cloud service, in the sense that different tenants of a cloud provider could bring their own packet processing programs, and the cloud provider could run these programs all together at line rate on the cloud provider's switches and network interface cards. Now, this capability doesn't exist today. This is the world we're trying to build towards. And this work appeared in a series of papers, and the lead PhD students were Ta Wang, who's a PhD student at NYU, co-advised by me and Arijit Panda, and Hong Zhu, who was a PhD student at Johns Hopkins, advised by Shinjin. And the focus of our work was high-speed packet processing pipelines. So you can think of these as ASICs dedicated to packet forwarding with some amount of additional flexibility added in to make them programmable for future use cases. And if some of you are familiar with these terms, this is the RMT or PISA architecture. If not, that's totally okay. I'm going to be reviewing some of these concepts in these slides anyway. So the reason we focused on these pipelines is they're rapidly emerging as the dominant architecture at the highest end for switches and NICs. So we're talking speeds of 400 gigabits per second on a single link on both switches and NICs, and there a streamlined pipeline for processing packets seems like the right architecture if you look at commercial products and the raw demands of processing packets at that speed. So these pipelines also don't have a processor, at least not for data plane purposes. They have a control processor, but that's not of too much interest here. But because they don't have a processor, you can't run an operating system that is the traditional way to achieve multi-tenancy. So the guiding question is, can we take multiple tenant programs along with the cloud provider's program and sort of make them coexist on the same packet processing pipeline? And what we need for this is a way to separate programs from each other, what the OS literature calls isolation mechanisms. So let's be more precise about this. What is isolation? So there are some requirements that you would find in an OS textbook. Okay, so one program cannot impact another program's behavior. If you change one program, like your Python file that you're currently iterating on, it shouldn't disrupt another program like your browser. And in the context of packet processing, we don't want the capability of isolation or multi-tenancy to add so much overhead that the overall throughput of the system is going to go down. Okay. And in the context of these pipelines that we're dealing with, one unique requirement is expressiveness, where the capability of multi-tenancy shouldn't come at the cost of how rich the packet processing programs that can be executed are. So I'll get into this expressivity over the next few slides. So before we do that, let me review how these pipelines operate, and then we'll talk about two strawman approaches to multi-tenancy or isolation, and then we'll talk about our own approach. So packets arrive as just a stream of bits. There's a parser that creates structure out of these bits by taking different bits and grouping them into headers, like an IP header, an Ethernet header, a TCP header. This vector of headers is called a packet header vector. And that is processed stage by stage in a pipeline. So you can imagine this giant column traveling through different pipeline stages. And what does each pipeline stage itself look like? So the input to the stage is a PHV. The first thing that happens is it's processed by a key extractor, which takes out a subset of headers from the PHV, concatenates them together to create a table key, which is then looked up in a table. And if that lookup succeeds, there is an action associated with that key in that table, and that action specifies how you transform the PHV using some compute units called arithmetic logic units or ALUs. And then this process just repeats itself across multiple pipeline stages. Okay. So against this figure, how would multi-tenancy work? So one approach is time sharing, the other is space sharing. Let's look at each in turn as strawman designs. So this is the same figure from before. For a tenant to control packet processing, it essentially needs to specify a configuration of how to parse packets, how to extract keys, what the contents of the match action tables are, and what the ALUs are. So it essentially has to specify the stuff that I just highlighted in orange. And to support multiple tenants, you must be able to change between one tenant's configuration of these orange blocks to another tenant's configuration of these orange blocks. And that turns out to be quite challenging to do at line rate because the size of this configuration is quite large and it's going to be hard to switch between one config and the next. So that's the difficulty with time sharing. The other approach is to share resources in space, where maybe, as an example, the first two stages go to the red tenant, the third stage onwards goes to the orange, or within a stage, a few action units or ALUs go to one tenant and a few go to the other. The problem with all of this is there is a limit to how much you can subdivide. You cannot subdivide less than one ALU or less than one stage. And that restricts either the total number of tenants that you can support, or each tenant ends up getting a very small number of resources. This is effectively like saying, if you have an 8-core processor, you can only support 8 processes because you're going to subdivide those 8 processors across those processes. So just to review, time sharing is too costly at high speeds, and space sharing reduces the number of units available to any single program, and that makes it limit expressivity. So we need a new approach that combines both, and that's what Menshen does in hardware. And it has 3 main ideas that have been lowered into hardware. So we evaluated this through an FPGA implementation and ASIC synthesis that shows that the area overheads of this are modest. There's more details in the paper. But the 3 main ideas are a tenant ID to represent the program that needs to be executing, time sharing, and space sharing, all in hardware. So let me get into each of these briefly. So the tenant ID identifies which program and which tenant we need to be using to process this packet. And every packet specifies the tenant ID in its header using the VLAN tag. And so this is what the packet format looks like. Okay. And in the context of a pipeline, what this physically means is we end up adding this TID to all of the PHVs as it travels through the pipeline. And this will, of course, have sort of ripple effects for the other units. And I'm going to discuss those briefly when I talk about time and space sharing in Menshen. So how does time sharing work? I'm going to illustrate this in the context of the key extractor. Again, the principle is more general. So the key extractor's job is to take out some headers from the PHV and group them to form the key. So it's essentially a multiplexer that does an n-to-1 reduction multiple times to create all the different parts of the key. So one way to configure the key extractor is to use the table ID, the tenant ID, sorry, to extract into a key extractor config table, which then configures the multiplexers in the key extractor, which pulls out various different components of the PHV to form the table key, which can then be looked up. Now, if we zoom in on the key extractor config table, this config table can be reused across multiple or time shared across multiple different tenants. You can get a packet with a yellow PID, and that would pick out a different configuration. The green PID would pick out a different configuration, and so on. So the dual to time sharing is space sharing, where for resources like the match action table, we can divide it up so that some number of entries are given to the orange tenant, some to the blue, some to the green. Now, there are 2 things that need to happen in hardware for this to work, first of all, the lookup to the match action table must now be based on a composite key that combines the tenant's key, which is the table key, with the tenant ID to form the entire key. And the match action table entries, again, the keys for that need to both have the tenant ID and the actual key entry. Now, based on this, you might look up an action entry that controls the ALUs. Now, we've applied this to other resources within the pipeline. I've just shown this in the context of a few resources, but there's many more details in the paper. So to review, what we do here is we identify programs using a tenant ID carried in every packet. So you can think of this as equivalent to a process ID in an OS. We do space sharing for relatively abundant resources like tables, where it's large enough that we can split them across multiple tenants without losing expressiveness. And for scarce resources like key extractors, where we don't have enough units to split up across programs, we just reuse that unit over time across multiple tenants using config tables, which are crucially in registers, which allows us to switch between tenant programs rapidly at per packet timescales. So beyond this project, we've used Menshen as a compiler target, which I'll talk about in the next part of the talk. And others, in particular, a group from the Max Planck Institute, have used it as a component when simulating future distributed systems. Okay, so let me move up the stack now and talk about system software. And here I'm going to be discussing a particular algorithm to generate code for packet processing pipelines. And the higher level thesis for this research is that using these solvers as building blocks in packet processing compilers gives us two benefits. One, in an engineering sense, it might be a lower effort way to develop compilers where the heavy lifting of a compiler is outsourced to a solver instead of having to manually do, say, code generation or resource allocation. And it's also a way to improve the quality of the resulting generated machine code because these solvers effectively are performing exhaustive search over a space of possibilities, which can lead to better quality code. Now, this is not a new observation. Other domains have benefited from it, in particular, say, databases have used synthesis in a variety of ways, DSPs. We think it's especially beneficial for packet processing because high performance, meaning hitting line rate and having really low latency, is critical. And it's also harder to find compiler developers for a niche target. And so using solvers to reduce the requirement for such compiler developers could provide interesting benefits in the long term. So this is based on a pair of papers, and the lead PhD student was Shangyu Gao, who's co-advised by me at NYU and Srinivas Narayana at Rutgers. And this was also a collaboration with Professor Aarti Gupta and her students at Princeton. So let's zoom into the underlying hardware for which we're doing code generation. So this is the same pipeline from before, but we're just going to focus on the ALUs, okay? So let's say the packet header vector has the following contents. It's processed by a parallel array of compute units called ALUs. Some of these might maintain state, like the two things on top. And the circles basically show the initial value of the state. And some of them might be purely stateless and operate just on packet headers. There's a giant operand crossbar that supplies the inputs to these various ALUs. And all of this is configured through what is called a very long instruction word that both specifies what operands to use for each of these ALUs, as well as what the opcode or the operation of each of the ALUs is. So as one example, let's say we pick the plus operation on all of the ALUs and we configure the operand crossbar in the following way. Then the output for the stateful ALUs, let's assume the output is just the sum of the input two operands plus the state. And for the stateless ALUs, let's just say it's the sum of the input operands. This is what the output would look like. And for the stateful ALUs in particular, we might have a separate operation that controls how the state itself is updated, potentially based on the packet headers that have come in. And let's just say that that operation was configured to be an increment. So 2 becomes 3 and 3 becomes 4. And this same process repeats itself. Okay. So there are two things interesting if you're a computer architect and are looking at this figure. One is state is local to an ALU. So these blue boxes, blue circles can be touched by one and only one stateful ALU. So you don't have this issue where state is read in one stage and written in another stage, where you could have stalls waiting for the state to be written back. And this is common in RISC or MIPS pipelines. You don't have that issue because state is local to a stage. At the same time, this poses some interesting constraints because the operations on that state need to complete within a single clock cycle, because each ALU is receiving a new packet every clock cycle. And you just need to be prepared to process the next packet without stalling the pipeline. But the benefit of this is those operations that finish within a single cycle, limited as they might be, are still atomic. So you get atomicity at the highest speed without requiring locks and the unpredictability that comes with lock contention and such. The stateless operations are sort of trivially atomic because they're not manipulating any state. Okay, so these requirements sort of bubble up to the compiler. So programming these pipelines turns out to be quite challenging. And this is an example in implementing SIP hash, which is a common keyed hash function that mitigates collision attacks on hash tables. So a group of researchers from Princeton managed to implement this on the Tofino programmable switch pipeline. And they wrote an entire paper describing that implementation because it required considerable manual effort. And the core issue, just paraphrasing from their own paper, is to take a complex computation like SIP hash and break it up into what happens in each stage. So the left-hand side here shows the SIP hash algorithm as maybe described in pseudocode. In Wikipedia, it's 14 sequential statements. And the right-hand side shows how it's broken down into what ALUs the Tofino switch actually provides. And they had to do this manually. So the question for our work is whether we can automate that arrow. So more precisely, this is the problem statement. We start out with a transactional spec of what we want to be executed on the pipeline. So the P4 language now supports this through its atomic construct, which was based on a prior project of mine called Domino. And SIP hash could be an example of the transactional spec. We couple it with a specification of the compute units, which says what the hardware is capable of. And that we represent using grammars. So for instance, we say that you could do an addition, min, or max on state variable, packet header, and a constant, and write it back into the state variable. That's the stateful ALU portion. And on the stateless side, we do the same set of 3 operations, except it's just on a pair of packet headers. So we feed all this into a compiler that needs to come back with something like this, which specifies what runs in each stage of the pipeline and how it maps to ALUs that are available in the pipeline. So obviously, when generating this pipeline implementation, you have to worry about dependencies. So p.f needs p.d to be computed. So this p.f statement cannot be scheduled before the p.d statement is scheduled. That's something you see in any compiler. The somewhat unique constraints here are to respect the limited ops of the ALU. On the stateful side, because state is entirely local to a single ALU, the compiler's job is to identify the stateful portions of the specification and map each stateful variable one-to-one to a single stateful ALU, such as this one on the top. And on the stateless side, because these operations by definition are atomic, we can have multiple stateless ALUs chained together in tree-like structures to form a stateless computation. But there we want to minimize the depth of the resulting circuit so that we minimize the number of stages needed. So how do we do this? The first thing is to cleanly separate out the stateful and the stateless portions of the spec. So we do this by taking the stateless portion in line 3 here and replacing it with a packet header. We replace the state S by the packet header p.new_s that reflects the fact that the state is updated in the second line and the updated value of the state p.new_s is carried to the third line. And now we're ready to separate out and separately map the stateful and the stateless portions. So let's put them on the top and bottom halves of the slide. And let's bring back the grammars that we're trying to map the stateful and stateless portions to. So the stateful portion, and in all of this, we end up using syntax-guided synthesis, where the syntax-guided portion refers to the fact that we're using grammars to control the search space of synthesis, and we use an off-the-shelf tool called Sketch to actually carry out the synthesis. So if we look just at the stateful piece, this Sketch solver comes back and says that the op is plus, the constant is 2, and p.x, meaning the input operand, is p.b. This is something that you could have figured out through pattern matching. This is just for illustration. We've been able to express much richer stateful grammars, including those found on real programmable switch pipelines and simulators of pipelines that we've built. On the stateless side, the problem is a little bit more challenging because it's no longer a one-to-one mapping. You can map the stateless computation on the left to an entire tree of stateless ALUs on the right. So we want to minimize the depth to reduce the number of stages, as we said a few slides ago. So the smallest possible depth is 1, just a single stateless ALU. Here, it turns out to be infeasible because this stateless computation needs multiple inputs, p.d, p.a, p.new_s, p.e, and so on. And that stateless ALU can only support 2 inputs. So we iterate by trying a tree of depth 2, which is a root ALU fed by 2 leaf ALUs, all drawn from the same grammar on this slide. And there, it's actually feasible. And the mapping is, again, what you would sort of naturally expect. But the principle here is much more general. We've been able to express more complex stateless grammars that include XOR operations, left shifts, right shifts, conditional additions where you might add 2 packet headers based on whether a predicate is true or not, and then write the result into a 3rd packet header, and so on. Okay. So we evaluated this by building 2 code generation backends, one for the quite well-known Tofino switch pipeline and another for the open source Menshen pipeline that we just discussed. In the process, we created many stateful benchmarks that are of independent interest. And the main takeaway is that we can generate high-quality code in reasonable time for this domain. And returning back to that SIP hash example that motivated all of this work, the authors of that paper were able to manually pipeline SIP hash, and we were able to automatically generate a 4-stage pipeline, so equal in depth to the author's implementation. The main drawback is on some examples like CAT, it takes 40 hours. So this is still reasonable if your code doesn't change too often, but you may want to improve it. We've looked into this, and special handling of bit vectors during the synthesis can reduce the synthesis time. So we believe there's quite a bit of room for improvement. This is something that is still open. Okay, so in the next part of the talk, I'll discuss how network flexibility can enhance distributed applications. And I'll discuss this in the context of a new multicast primitive based on synchronized clocks called deadline ordered multicast, and its implications for distributed consensus and fair access stock exchanges on the cloud. So this was based on a pair of papers. The first was led by Jinkun Geng, who was a PhD student at Stanford, who I co-advised, and the second by Ahmad Ghalaini, who's another PhD student at Stanford I closely worked with. So the traditional way in which distributed systems and networks have interacted, just to set context for this work, is, they've almost had this arm's length relationship where there's some very, very bare contract where the distributed system doesn't assume that the network does anything more than eventually deliver packets. And this very much reflects the internet ethos as well. And this conservative view of the network leaves quite a bit of performance on the table, because the network could provide more services that are more directly aligned with what the distributed system needs, but not using or not providing these services leaves quite a bit of performance on the table. So there's been a long-running quest, starting with the ISIS toolkit and Ken Berman's work at Cornell in the 90s, where the network could provide more services to the distributed system. More recently, researchers at UW have looked at using programmable switches to provide these services and improving distributed systems as a result. So we take a lot of inspiration from all of these lines of work. The point of departure for our view on the problem is, can we do this without requiring new hardware for switches or NICs, so that we can provide immediate value to cloud tenants while programmable switches and NICs are still in the process of getting more widely used? So the answer we came up with is a new multicast primitive called deadline ordered multicast, and it works as follows. We have a sender and multiple receivers. So that's just the setup for multicast in general. They're all synchronized to the same clock. We use a clock sync algorithm from this company called Clockwork, which I'm an advisor for. The sender then creates a message and attaches a deadline to that message, and it uses some kind of application library to create multiple unicast messages and send this to all of the intended receivers. Now in the cloud, message paths are entirely unpredictable, so these messages could arrive at the receivers at various different times. So R1 and R4 at 5, R3 at 6, R7, Rn at 7, and R2 at 8. Point is, all of this is unpredictable. But at time 9, which is the deadline specified on the message, all the receivers simultaneously decide to process the message, simultaneously modulo some clock error. Okay. And once you process a message as a receiver, you can't go back and process a message with the previous deadline. This is where the deadline ordering comes from. And the deadline itself is an estimate of when the message would have reached the receiver. So concretely, it's the send time plus an estimate of the sender to receiver delay. So what is this good for? The conceptually simplest example is fairness in the context of stock exchanges in the cloud. So very briefly, the way a stock exchange works is there's a central exchange server which periodically disseminates prices of stocks called market data to traders through these gateways. And to ensure fairness, this market data should arrive at roughly the same time at all the traders. So the way the exchanges do this is to literally measure out cable lengths from the central exchange server to the gateways. So on the cloud, where you can't do all of this cable measurement because you don't see the cables, we can use clock sync through DOM, where the exchange server can DOM multicast a message with the deadline being the time at which the gateways are allowed to release it to the traders. Now, the second place in which it's helpful is a more involved use of DOM. And that is in consensus protocols, where if DOM has been able to successfully multicast a sequence of client requests to a replicated state machine, and all of them reach before their request deadlines, then the replicas can agree on a request order, which is exactly the deadline order, without having to talk to each other. Okay. And this gives you a fast path to reach consensus quickly, in the same style as protocols like fastpaxos, if some of you are familiar with that. But the point is, you can reach consensus faster under sort of ideal conditions. But of course, things are not ideal all the time. So you need a slow path in case messages arrive after their deadline or they're just dropped altogether, where a leader needs to talk to the followers and sort of decide unilaterally on an order of the ordered log. So the interesting idea here is we delay processing of the requests until their deadline, and that allows us to take the fast path more often, and that actually counterintuitively improves consensus latency. And we're currently applying this to concurrency control and DFT, where there's protocols with a similar fast path versus slow path structure. So how does this fit in with programmable networks? So DOM is something that the network needs to be programmed to provide as a service. So one way you could do this is to use switch support for multicast, to synchronize clocks across switches using programmable switches, as people have done. What we do is a different kind of network programmability, sort of similar to overlay networking techniques from the early 2000s, where we use a proxy VM interposing between the sender and the receiver VM. So the sender sends its message to the proxy, which essentially multicasts it to the receivers. And this is how we implement DOM. And this has a couple of interesting benefits. First of all, the proxy performs the multicast on the sender's behalf, and it reduces the sender's CPU utilization. The proxies can be time synced with the receivers. The senders don't even need to worry about time sync, which makes it easier for clients to just operate as they would have with an existing consensus protocol. They're stateless, which helps with scalability and fault tolerance. Just a note, the deadline is now going to change to the arrival time at proxy plus one-way delay from proxy to receiver. Essentially, this is an application layer middle box. Okay. So we evaluated by comparing to three pretty well-known baselines, or rather, I'm just going to show you three here. There are many more in our paper. The workload is as follows, and we had two versions of Nerja, one in which the client directly does the multicast and another in which the proxy does it. This was all run in Google Cloud. I want to stress here that we don't expect Nerja to provide benefits in a cluster with programmable switches and NICs. Okay. So in such a situation, a protocol like NoPaxos that uses programmable switch support for sequencing packets would benefit better. Our point is, in the public cloud where you don't have such features yet, you're going to get a significant win. We have many more extensive evaluations in the paper. But just briefly, when we compare against protocols like fastpaxos and multipaxos, and all of them leave the final copy of the data in memory, we see a substantial performance benefit. And the proxy does increase latency. So at any point here, you can see that the proxy's curve is higher than the client-only curve, but it saves client CPU. We compared with Raft, and for this, we had to adapt Nerja to persist data to disk, because that's what all the Raft implementations do. And again, there's a performance improvement, but you'll notice here that the latency is in the milliseconds range as opposed to here where the latency is in the microseconds range. So again, there's a big performance improvement. So I'll now just briefly touch on a future direction that we're particularly excited about, and that's this idea of moving programmable processing from processing over packets to processing over units of data that are of direct relevance to an application, such as an RPC. So this is motivated by the fact that apps are getting increasingly distributed, where they're turning into modules like microservices that communicate over RPCs. We see this with ML training, with frameworks like Ray. And in all of these contexts, communication should ideally be invisible, where no one should be aware as the application developer of the costs of communication or queues or congestion and things like that. In other words, we do our job best as networking researchers if the network essentially remains invisible. But it isn't today. This is far from the case. Distributed apps pay a significant communication tax. This is a phrase from a well-known paper from ISCA 2015. And this tax includes a bunch of stuff that sit between the application generating the data to the point packets go out of the wire. So it includes stuff like serialization, encryption, congestion in the PCIe interconnect, and so on. And this tax, from the application's perspective, adds latency, and from a resource efficiency perspective, takes away CPU cycles that could be used for other things. So the guiding question for this work is, can we bundle up all of this tax and move it into specialized hardware where it can be executed more resource efficiently and improve latency in the process? So the cartoon depiction of this worldview is the application generates RPCs, the RPC processor does a bunch of stuff, and outcome packets at the other end. We have some very early results with FPGAs. This is again led by Tao Wang, who was the PhD student who led the Menshen work as well. And we see significant latency savings from offloading request load balancing from software into hardware. And the early learning is that this isn't just about taking an existing abstraction and moving it into hardware. That turns out to be both very challenging and also not required to satisfy our higher level goals. Instead, we find that reimagining the intermediate abstractions, for instance, using message-based transport instead of byte streams, allows us to actually build hardware-friendly designs. So our long-term plan is to prototype this as an ASIC and make it more broadly available. And I'm particularly interested in some of the recent momentum around open source hardware designs, where some of these components of an RPC processor could be interesting class projects. So what can this enable? Really, I think any workload limited by communication latency is an interesting use for this. And there are many connections to other areas of computer science, because once you build the hardware, you get to reimagine the software stack on top. And to wrap up, I want to leave you with 4 key takeaways. One is judiciously designed new hardware gives us both flexibility and performance in packet processing. Solver techniques will play an important role when designing compilers for this hardware. Network flexibility can improve distributed applications. And for the next set of advances in programmable network hardware, we should move up the stack, where we look at programmable processing of application data units like RPCs instead of packets. So with that, I'll wrap up. I'm more than happy to take questions. Yeah, thank you for your time.
Thank you, Professor Sivaraman, for an informative talk. We have time, we can take few questions.
Yeah, go ahead.
Yeah, so we wish we could have a 3-hour or full day session based on this topic. It was quite heavy in content. So starting with the last one, what would be required for these RPC-based messaging semantics to enable it in the core of the networks?
Yeah, that's a great question. We weren't imagining moving RPCs as such in the core. So the core would just see packets in the current view that we have for this RPC processor. So the RPC processor is effectively a replacement for a traditional NIC. So the cables and the core switches and the routers would still see packets. I think it's an interesting question whether those could also be refactored to deal with RPCs. I mean, I suppose in some ways, technologies like, I don't know for sure, but technologies like RDMA to some extent do this because they deal with sort of more application relevant pieces of data throughout the entire fabric. But we were thinking about this as purely something on the host side before packets are generated for the rest of the network.
If I can ask another question. So, multicast part, like it has been around for like decades, and like now you're also talking about DOM, but what changes are required for enabling this DOM from the network infrastructure or IP layer side?
Yeah, so that's a really interesting question. It's certainly something we've thought about as future work. So what we've currently done is entirely operate at the application level. But to your question, if you were to do it on the infrastructure side, you'd need a couple of things. One is sort of fine-grained clock synchronization, which you could do using a protocol like PTP. Then you need switch support for multicast, which exists on most switches today. It's not a very commonly used feature outside of the financial industry, but I think it would basically be a combination of PTP plus IP multicast inside the switches. There are some restrictions on this network infrastructure type approach because the number of multicast groups that you can support on a switch is somewhat limited. So if you have many multicast groups, you might somehow run out of steam. But there's work that leverages programmable switches, in particular this project called Elmo out of Princeton, to address this multicast scalability limitation with hardware switches. Yeah, but that's I think how you would implement it. And I think that's an interesting problem to bring all of that together for a more high performance implementation of DOM than what we have currently.
Thank you.
Yeah, so there was a question about why time synchronization is implemented as an application on the host OS instead of on the switch or NIC. Yeah, so there's a few ways to answer that. One is, implementing it purely on the host OS makes it easier to deploy in these cloud environments where you don't have access to the NIC in most cases. There's a small set of exceptions which I'll get to shortly, but that it makes it much easier to implement in cloud-like environments. At the same time, if the cloud provider exposes some NIC information, for instance, some clouds expose timestamps of packets when they cross the NIC, you can leverage that information to improve the accuracy of the same Huygens or clockwork algorithm that we used. But the reason to implement it as an application on the host OS by default is mostly just about easier deployability. And it does degrade the accuracy a little bit, but so just to give you a sense of it, we get few hundreds of nanoseconds with host-based timestamps and probably an order of magnitude less, so tens of nanoseconds clock sync error with switch or NIC. With NIC timestamps, with switch timestamps, you can do even better. We don't go there. So we do lose some synchronization accuracy, but it helps with deployability significantly. Yeah, these were really great questions. Any other questions?
So just I have one question. So I didn't quite follow when you were doing this automating the the processing you're doing for solver techniques, right? For the compiler. And you said so I understood the logic that you can do it manually and you would require a lot of thinking to decide in which order you'll do it, right?
Right.
But what is the technique you're using to automate? I didn't quite understand how you automate it.
Yeah, let me maybe just briefly review it. So there's some pre-processing steps that are in our papers, but I didn't get to. But let me just go over the core ideas. So at the highest level, what we're trying to do is, we have this specification from before, like the specification from this slide. We've taken it as such and put it on this second slide. So there's some amount of pre-processing we need to do, some of which I didn't mention here for simplicity, involving strongly connected components to find cycles in the graph to identify stateful computations. But assuming the stateful computations have been identified like this, what we're trying to do effectively is to take the stateful computation and find a stateful ALU to implement it in its entirety. And then we're taking all the surrounding stateless computation, meaning the computation that creates P.F. Maybe I can highlight it with my, here, pen. Okay, so P.F, the computation that creates P.F. And that involves, computing P.D before that, and then P.A before that, and all of that forms a DAG for the stateless side. So then we have this stateful and stateless computation that need to be mapped to the underlying ALUs. And the ALUs have this grammar that specifies what they can do. Okay, so the ALUs can do a plus or a min or a max. So we need a search procedure in general. Like for this particular example, it's very straightforward to do it manually. But in general, we want a search procedure to search over the space of possibilities allowed by the grammar. And that's where syntax guided synthesis comes in.
I see. So actually the pre-processing is the very important component of it, right? So discover the graph itself, and then sort of trying to simplify it, right? That if multiple stages can be merged into one, and then that output can go into the next stage and things like that, right? So
yeah, so the pre-processing is important. It's relatively standard techniques that we use there. If you're familiar with the literature on software pipelining from the 80s in the context of VLIW machines, we use some of those techniques. So we basically draw dependencies and find loop carried dependencies. And all of that essentially separates out the stateful from the stateless. Yeah, the pre-processing is definitely important. The synthesis is sort of the new piece.
I see. So second question I had was on the your DOM. Actually, I think this when you do this delay ordered.
Deadline ordered, yes.
Deadline ordered. So yeah. So in this, I understood. So you this is what my understanding is, that you sort of want to estimate what is the worst possible delay you would see across all of these receivers, I guess, right? So that you also don't want people to wait, right? So you will say I send something and by this time everybody should order, so they sort of reply to you again. But again, the reply could also be delayed, right? So suppose your deadline is 9 and they all send, but you might still get R1 at 11 but Rn as 15, right? So there'll still be non-synchronization. You'll have to wait for everyone else to respond as well.
So the primitive that I described here only deals with the forward path from the sender to the receiver.
Not from the receiver.
Yeah, so we don't worry about exactly how we process replies from the receiver as part of the primitive.
I see.
We do have to deal with it. If a client doesn't get a response from a replica, it eventually has to time out and retry the request. And that's all part of the consensus protocol, NERJA, that builds on top of DOM. But the primitive itself doesn't deal with that. But I will say one thing though, which is, this deadline needs to be set somewhat conservatively, as you said, like so that the last of the receivers, the worst of them gets it. But if you're too conservative and say that the deadline is 1 hour into the future, then you're just going to wait around endlessly. So at that point, you don't get any benefits from the fast path. So there's an interesting trade-off there between.
Got it.
Yeah.
So just one quick question. Suppose your primitive was the both side communication, like going from sender to receiver and back. instead of putting deadline on the receiver, you might as well just put a deadline on the sender itself, the time until I receive, right? And then whatever response you get in this time, is like, I'll work with this, right? And I'll just throw everything else. So you get whenever you get, then you process, and only when I receive, I decide what to do.
Right. So I think that kind of primitive where you wait for the response to come back, as you suggested, could help with certain kinds of applications. I don't know if it is totally well aligned with what we need to do here for consensus, because for our use cases, the deadline provides an amount of time to wait so that each receiver knows that with high probability the message has reached the other receivers, and so it is good to process it. And then you can basically,
so the one negative with that is that we can also take this offline if you want, but the so suppose your worst deadline was really 8, right? And then you're making them wait 1 extra. But if you did not say that, right, and you just go to the sender, and sender can also not put deadline in terms of the time, but it can also put deadline in terms of the number, right? It probably would save a little bit more time in the amount of time it's waiting. But yeah, you're right. Depends on the application you're interested in.
Yeah, exactly. So I think we'd have to think about how a different primitive would then result in a different protocol. So, we found this primitive to be simple enough to implement and also usable for a range of protocols that have this fast path, slow path structure, and also for these stock exchange type applications where you want simultaneous release of data. But yeah, I think there's an interesting space there for sure to explore richer primitives and what their implications on protocols are.
Thanks, Anirudh. That's all my questions.
Okay, so when you say 10 nanoseconds for switch level time sync and 100 nanoseconds, what is the typical physical distance? Okay, that's an interesting question. So I don't know the numbers concretely. I will say that all of this is referring to experiments within a single cloud zone. So imagine like a data center building, which is, typically the size of a few football fields in American football fields. So I don't know, several hundred meters could be the longest distance between a pair of physical machines onto which the VMs are scheduled. So the accuracy is both this 10 and 100 nanoseconds degrade when you go across the wide area. They get like about an order of magnitude worse. And I should say though that the 10 nanoseconds is using NIC level timestamps and 100 nanoseconds is using host level timestamps. It's not switch for 10 nanoseconds. But yeah, the physical distance is typically the distance within a data center building. Any other questions?
If there are no more questions, we can close this session.
Thank you all for your time. And yeah, I'm happy to take more questions offline or email. Oh yeah, there's another question. I guess two questions.
One more question. So with for the programmable network devices, what's the currently preferred platform now that Tofino is discontinued and like we don't have any new P4 compliant switches being launched?
Yeah, so there's a few possibilities. One is, first I should say that I think the status of that is, Tofino 1 and 2 will still be produced, but there's no roadmap for future versions of the chip. So you may not get like higher speeds over the next 3-4 years, but you still get to use like, 12 terabits per second or whatever was the Tofino 2 speed. But beyond Tofino, there's products from other vendors like Broadcom, like the Trident and Jericho lines, from Mellanox, like the Spectrum line. The Broadcom ones are programmable in NPL. The Mellanox ones I'm not sure about. So that's on the switch side. There's been some interest in attaching a coprocessor to the switch where, you send certain packets out of the output port of the switch into like an FPGA, do some programmable packet processing through that, and then send it out of the FPGA. So this is this bump in the wire type architecture where you add an FPGA to a switch, or honestly, you can add it to a network interface card or host as well. And there's certainly a lot of interest doing stuff on smart NICs, like the Intel Mount Evans, is the Pensando smart NIC. So there's a couple of different alternatives. Yeah, so that's the state of things.
Thank you.
Okay,
So-
there is one more question from the chat.
Just
With
saw that.
application-based synchronization, the host NIC latency also reduces the accuracy. Is this latency taken into the consideration? How do you overcome this?
Yeah, it's definitely taken into consideration. So the way the clock sync algorithm works is, you take timestamps at the point at which you send the message in the host and the point at which you receive the message in the host. And, if you had NIC timestamps, both the send and receive timestamps would be replaced by the send NIC timestamp and the receive NIC timestamp. So the host to NIC latency does show up in the way the timestamps are taken, and it does affect accuracy and it reduces accuracy. This is the 100 versus 10 nanoseconds gap that I was talking about. And there's no easy way to overcome this. Typically, the longer the latency between 2 points, roughly speaking, it also correlates with latency variability being higher. And that does mean clock synchronization accuracy is going to be lower. And there's some fundamental results in distributed algorithms going back to the 80s that talk about how clock sync accuracy is tied to variability in latencies. And so, yeah, wide area versus wide area accuracy tends to be lower. Accuracy with host timestamps tends to be better than that, but lower than accuracy with NIC-based timestamps. Yeah. And if you have switch timestamps like PTP does, you can get even better accuracy. Any other questions? Yeah, go ahead. I can hear an echo.
Sorry. So what I wanted to ask with that question was not host-based timestamps and NIC-based timestamps separately, but the time it takes for a packet to travel from the host up to when it gets timestamped at the NIC. So there is usually a time that it takes when a packet traverses through that. So how is that taken into consideration? While...
Oh, I see.
Okay, yeah.
Okay, I think I get your question. So you could do a two-step procedure where you synchronize the clocks of all the network interface cards using NIC-based timestamps using this Huygens algorithm. And then you have a separate local synchronization procedure where you deal with just the host to NIC latency and back, where you synchronize the host clock with its NIC clock. So you have sort of this global synchronization of the NIC clocks across all the servers, and then you have this local clock synchronization between the host and its NIC clock.
No, interesting. Thank you. Yeah. Sorry.
Okay. Okay. Sorry, I just heard an echo. Okay.
Okay,
Yeah,
I think we can close this
questions.
session.
Yeah, thank you so much. Yeah.
Thank you, Professor Sivaraman, for this informative talk. And thank you all. Have a great evening. And this video will be available in our website. Thank you.